Most of us think we understand light, but the more we study it, the stranger it becomes. Because here, light doesn't just interact with matter, it can blend with it. In rare conditions, light can merge with particles of matter to form something entirely new. Not just a photon, not just an electron, but a hybrid. A ripple between worlds. And when it does, it can start behaving in ways we don't expect, flowing like a liquid, spinning like a vortex, or even mimicking the structure of space itself. These hybrids, known as light-matter quasi-particles, are quietly reshaping how we think about physics, technology, and maybe even life. In this video, we're going to explore what they are, how they form, what they might be capable of, and how this implication ripples outward in some truly fascinating ways. Just wait. From condensed matter labs to quantum optics, from biosensing to black hole analogs, these strange hybrids are showing us that the boundary between light and matter may not be a boundary at all. If you're new here, welcome. Please subscribe. Everyone hit the like button, and I'm going to link a couple of videos at the end that I think will pique your interest after this one. But for now, let's just begin with what exactly is a light-matter hybrid. To understand light-matter hybrids, we need to shift how we think about particles. We often imagine them as discrete entities, photons, electrons, atoms, each with a clearish identity and behavior. But in physics, there's another category, quasiparticles. A quasiparticle is not a fundamental building block. It's a phenomenon, an emergent pattern that behaves like a particle, but only exists because of the collective behavior of a system. Think of a ripple in a pond. It's not the water, it's not the wind, it's the motion, a relationship between the two. Light-matter hybrids are this kind of ripple. They form when a photon, the basic unit of light, couples with some form of matter. And that coupling, as you will see in a moment, can take different forms. But regardless of the form, each hybrid is a kind of temporary alliance. The photon lends its energy, the material provides a structure, and together, they become something new. And what makes this more than a curiosity is what these hybrids can do. Because when light enters into a relationship with matter like this, it can slow down, acquire mass, or behave in ways we usually only associate with condensed matter systems. They're not just tools for studying exotic physics, they're tools for reshaping it. So now that we understand what they are, let's look at one of the most intriguing examples, the polariton, a particle that flows like light but behaves like matter. The polariton forms when a photon enters a specifically designed cavity and strongly couples with an exciton. That is, a bound pair of an electron and the empty space it left behind, known as a hole. These pairs, electron and hole, can briefly act like a single particle, and under the right conditions, they can interact with light so strongly that something new emerges. The coupling is so intense that the photon no longer simply bounces around. It becomes entangled with the exciton. The two cannot be separated without destroying the hybrid itself, and what you get is not light anymore, and it isn't matter. It's something in between. Polaritons can do something unusual for a particle made partly of light. They can slow down, they can interact, and under certain conditions, they can even condense into a macroscopic quantum state. In other words, they can form a kind of fluid, a liquid not made of atoms but of quasi-particles. And this fluid doesn't behave like anything else we see in everyday life. In some experiments, polaritons flow with zero resistance, forming what's called a superfluid. In others, they spontaneously organize into quantum vortices, like miniature galaxies made of light. What makes this especially astonishing is that these effects don't always require extreme conditions. Unlike most Bose-Einstein condensates, which form near absolute zero, some polariton condensates have been created at room temperature using organic semiconductors or special layered materials. This means we're no longer confined to the coldest corners of physics to study macroscopic quantum effects. Polaritons are now being investigated for use in photonic circuits that could replace or enhance silicon, quantum simulators that model complex systems using light, and even ultra-low power computing, where information flows not through wires but through coherent waves. If something can flow like light but behave like matter, could it help us understand the boundary between them, or even model something deeper, like the fabric that connects them both? We'll come back to that idea later, but first, let's look at another kind of hybrid, one that doesn't just flow, but focuses. Now it's time to meet the plasmon. A plasmon is a light-matter hybrid that forms when photons couple with surface electrons. A plasmon is a light-matter hybrid that forms when photons couple with surface electrons, in particular the collective motion of electrons along a metal's surface. Instead of simply reflecting or passing through, light can interact with these surface electrons and set them into motion. The result is a new kind of wave, bound tightly to the material, part light, part charge oscillation, and this wave behaves unlike ordinary light. Traditional optics are constrained by something called the diffraction limit, a kind of lower bound on how tightly light can be focused. Plasmons break through that limit. They compress light into regions smaller than its own wavelength, allowing us to concentrate energy into nanoscale volumes. The ability to confine and manipulate light at such small scales has opened new frontiers in science and technology. Plasmonics is now being used in biosensors capable of detecting a single molecule, cancer diagnostics that use light to identify disease markers, solar panels that capture more energy by scattering light at the nanoscale, imaging systems that reveal structures too small for traditional lenses to resolve, and beyond sensing and imaging, plasmons are being explored in quantum optics, ultrafast communication, and even next-generation computing, where information could be guided and processed through patterns of light instead of electrical currents. If we can focus light this precisely, if we can sculpt fields at the edge of the atomic scale, then what else might be possible? We will dive into this question in just a bit, because first we need to meet the rest of the hybrid family. Quasiparticles that don't just flow or focus, but twist, vibrate, and ripple in ways that blur the line between physics and design. Physicists have uncovered an extended kind of family, each one formed from a different kind of interaction. Each one reveals a new way that light can behave when it merges with the structure of matter. Let's meet a few of the lesser-known members. Phonon polaritons emerge when photons, particles of light, interact with optical phonons, which are quantized lattice vibrations in a crystal. This interaction creates a new quasi-particle that shares properties of both light and matter. These hybrids are especially prominent in the infrared and terahertz frequency ranges, where they can carry not only electromagnetic signals, but also vibrational energy, essentially allowing light to ride the atomic scale tremors of a material. Because of their dual nature, phonon polaritons are incredibly efficient at confined energy transport at the nanoscale. They can propagate signals with minimal heat loss, making them valuable for thermal nano devices. like heat managing components and microchips. Their ability to interact with vibrational modes also allows them to encode both optical and thermal information in a single wave. Perhaps most intriguingly, phonon polaritons can achieve sub-diffraction resolution, meaning they can carry information at scales smaller than the wavelength of light. This makes them ideal for deep sensing, infrared imaging, and nanospectroscopy, where traditional light waves would be too large. Next up is the Magnon polaritons. These are quasiparticles formed when photons couple with magnons, the quantum units of spin waves, which are tiny ripples in the magnetic alignment of a material. This interaction creates a hybrid that combines the electromagnetic nature of light with the magnetic properties of matter. What makes Magnon polaritons so compelling is their ability to carry information not through electrical charge, but through spin, making them central to emerging fields like spintronics and quantum magnonics. These hybrids can travel with low energy loss and in some designs even carry quantum information, making them candidates for future technologies like ultra-efficient memory, signal processing, and quantum communication. And lastly, let's see what happens in ultra-thin materials like graphene. Here, strange new hybrids emerge from the quantum dance between particles. One of the most intriguing is the Plasmaron, a quasi-particle formed when an electron couples with plasmons, which are collective oscillations of the electron sea. This interaction reveals strong, many-body effects that go beyond simple particle behavior. Plasmarons have been detected in angle-resolved photoemission spectroscopy. They offer a window into exotic electron dynamics in two-dimensional systems. In graphene, where electrons move almost like massless particles, these hybrids reveal how charge, vibration, and interaction ripple together across a quantum sheet. These states are more than curiosities. They help physicists test the limits of quantum theory in condensed matter and may one day lead to new ways to manipulate light and charge at the smallest scales. Overall, these quasi-particles help us go beyond what light can do on its own or what matter can do in isolation. Together, they offer a toolkit for exploring interactions that were once thought impossible to observe. So now that we've met the family, let's go deeper and look at what these hybrids might be hinting at about the deep structure of reality. By now, we have seen how light can form hybrids with matter that flow like superfluids, spin like vortices, or vibrate like the lattice of a crystal. These are not theoretical. They're being made in the lab, controlled, manipulated, and used. What's striking is what some labs are attempting to do. We're going to go into that next. What some researchers are trying, what they think is possible, and what is just pure idea and speculation. Because light-matter hybrids are not just tools for nanoscale sensing or faster computing. They are starting to be used as models of the universe itself. In a series of experiments, physicists have arranged polaritons in carefully engineered optical lattices, systems where photons are trapped in microcavities and strongly coupled to excitons. But instead of just watching the particles move, they began warping the geometry of the space around them. By adjusting the structure and potential of the cavities, they created conditions where light inside the system behaves as if it is in curved space-time. What emerged were analogs of gravity. Polaritons flowed as though they were sliding along the contours of a gravitational field. even forming behavior similar to a horizon where excitations could not escape. Some researchers have used these polariton lattices to simulate black hole event horizons, where quantum fluids of light slow and stretch in ways that mimic time dilation and Hawking radiation effects. They are now working on creating topological polariton structures, hybrids that are immune to disorder and may let us study non-trivial curvature and edge state physics in ways gravity analogs alone couldn't. Meanwhile, another set of researchers is using plasmonic nanostructures, those tight electron-coupled oscillations on metal surfaces, to look for something even more elusive: dark matter. These systems are extremely sensitive under vacuum and at cryogenic temperatures. Even a tiny energy change that might come from a dark matter particle could shift their plasmon resonance. Experiments like spheres, quarks, and others are now exploring whether hybrid plasmonic systems might act as resonant detectors for particles that weakly interact with normal matter, like axions or other light mass dark matter candidates. In some designs, researchers are embedding magnonic or dielectric layers into these structures, creating multi-hybrid systems that combine electric, magnetic, and optical sensitivities, all tuned to respond if something unknown passes through. And every year, the detection threshold gets better. Then there are Magnon Polaritons. Those hybrids form from light and spin waves and magnetized materials. At first, they seemed promising candidates for quantum information systems, but recently, something more interesting emerged. Physicists realized that by entangling multiple Magnon Polaritons across a structured material, they could simulate behavior seen in quantum field theories, specifically how entangled regions in space can behave like connected networks, even when physically separated. This connects directly to research in holographic theory, and sometimes called ER equals EPR. That stands for Einstein-Rosen equals Einstein-Podolsky-Rosen, and it's the idea that entanglement and the shape of space-time might actually be two sides of the same thing. Some labs are now designing programmable spin lattices that let researchers explore how information might flow through these hybrid fields, essentially creating a tabletop model for what entanglement might look like if it built space-time instead of simply traveling through it. They're not just studying particles anymore. They're studying relationships, and whether these relationships themselves might be the root of reality. Each of these experiments takes a different approach, but all share a quiet implication that what we call empty space may not be so empty, that gravity, vacuum structure, even time might be emergent phenomena, arising not from fixed laws, but from the dance of interacting fields, and that light matter hybrids might just be the clearest language we have to start asking what reality is made of. We've seen how light matter hybrids are being used to model black holes, simulate quantum fields, and search for the invisible. But what if these strange couplings weren't just tools of high physics? What if they're already at work inside us? Because light doesn't only live in lasers or cavities, it also lives in cells. Now let's take a look at some theoretical ways this new information might be used in future research. You see, for nearly a century, researchers have observed ultra-weak photon emissions called biophotons, light emerging from living organisms. These aren't thermal or accidental. This light is coherent, sometimes pulsed, and carriers of information we are not quite sure how to read yet. These ideas were once pure speculation, but today labs around the world are exploring whether biophotons play a role in neural signaling, immune coordination, and cellular repair. And the more we study them, the more something interesting emerges. And these light matter hybrids might just play a future role. If you want to learn more about biophotons, check out the video I just did last week. I'll link it at the end of this video as well. Now let's hypothesize how this might play a role with structured water. Inside every cell, water isn't just bulk fluid. It forms layers, structured zones, especially around membranes and proteins. This form of water has been shown to have different electrical properties, different refractive behavior, and maybe even act like a semi-ordered lattice. Sound familiar? Some researchers have proposed that this structured water could support plasmon-like surface waves, oscillations not on metal, but on biological surfaces. If true, these water layers could form a kind of living photonic interface, guiding, modulating, or even confining light inside cells. It's not proven yet, but it's being tested. And it would explain how weak light could persist, travel, and interact far beyond what scattering alone would allow. Last but not least, there's growing evidence that certain amino acids, like tryptophan, show signs of collective light behavior, a phenomenon called superradiance or quantum coherence that normally only show up in condensed matter systems. And some biophysicists are exploring whether structures like microtubules, DNA helices, or mitochondrial membranes could serve as natural waveguides, shaping how biophotons move, much like engineered optical cavities shape photons in hybrid devices. These are not confirmed mechanisms, but they're grounded in measurable behavior, and they invite different ways of seeing. Maybe light in the body is not just a side effect. Maybe it's a medium for signaling structure and self-organization. We have seen that when light merges with matter in the lab, it gains new properties: mass, flow, coherence, and structure. What if life found a way to do the same? What if cells over billions of years learned to shape light the way physicists do in mirrored lattices and nano cavities, not for engineering, but for being? We don't know yet, so be sure to subscribe and hit notifications to stay in the loop on all of this and more. Because as we continue exploring the frontier between light and matter, biology might have more to do with it than most people expect. Now let's take a moment to pull it all together. We started with Polaritons, hybrids that flow like light but behave like matter, forming quantum fluids and even superfluids. Then we met Plasmons, where light binds to surface electrons and becomes tightly focused, small enough to sense single molecules or reshape solar energy. We explored Phonon Polaritons, which ride the vibrations of a crystal and let us guide heat like information. Then there was Magnon Polaritons, where light merges with spin waves in magnetic materials, opening doors to spin-based memory and quantum logic. And last but not least, Plasmarons, strange hybrids inside graphene, revealing how electrons behave when they no longer act alone. Each of these is not just a particle, it is a relationship, a pattern that emerges when light and matter meet in the right conditions. Together, they are teaching us how to bend light, simulate gravity, detect the invisible, and maybe even understand what cells and consciousness are really doing. We've only just begun. It is a great time to be alive and explore science and all of its implications. Here at Biolumination, we explore the places where science still whispers, but yet some of the most important questions are just starting to be asked. I sure appreciate all of your time. I hope you learned something new and see the world slightly different. I can't wait to read in the comments what each of you think. Be sure you have subscribed, hit the like button, share it with a curious mind. And most importantly, until next time, take care.